Every analog transmission begins as a clear, defined signal, but it is inevitably degraded by physical interference before it reaches its destination. In communication theory, we define noise as any unknown signal that interferes with the recovery of the desired message. The standard approach to modeling this interference is to treat it as an additive distortion. This creates a direct linear relationship where the received signal, R of t, is the mathematical sum of the transmitted signal, S of t, and the noise, W of t. We specifically identify this W of t as white Gaussian noise, which represents the thermal noise generated within the receiver's own front-end hardware. Because the noise is simply added to the signal, isolating the original message requires us to analyze the mathematical interaction between these two combined waveforms. Since additive noise is inherent to the received signal, measuring the absolute strength of R of t alone cannot determine communication quality. The viability of the system depends instead on the ratio between the intended signal and the unwanted noise. This ratio is the signal-to-noise ratio, or SNR, which we calculate by dividing signal power by noise power. A primary objective for a communication engineer is to maximize this SNR value to ensure the message remains clear. Logically, this involves two potential paths: increasing the signal power in the numerator or decreasing the noise power in the denominator. While increasing signal power seems direct, specific physical and economic boundaries usually shift the engineering focus toward the noise component. We trace the input message, M of t, through a standard block diagram of the communication system. First, the transmitter processes and sends it across the physical channel. Noise is added here at the summing junction, merging with the transmitted signal. From this point forward, the waveform entering the receiver is officially corrupted by that additive term. This raises a practical question. If the noise is added in the channel, why not simply use a more powerful transmitter to overwhelm it? The brute force approach of increasing transmitter power is restricted by three specific constraints. In theory, SNR improves as we increase the transmitted power, ST. In practice, however, the maximum value of ST is strictly capped by external factors. The first factor is equipment cost. High-power amplifiers require more expensive hardware and specialized cooling systems. Next is channel capacity. Every physical medium has a limit to how much energy it can carry before the signal begins to degrade. Finally, there is the risk of interference. Excessively high power can cause the signal to bleed into adjacent frequency bands, disrupting other users. Because the numerator is locked by these constraints, the only way to optimize SNR is to focus on minimizing receiver noise. To see how this is done, we look at the internal architecture of the receiver, which must process the incoming signal and noise. Before the signal is demodulated, it passes through a bandpass filter at the very front end. This filter serves as a gatekeeper, determining exactly how much of that additive noise is allowed to enter the rest of the system. To understand how the filter limits noise, we look at the signal in the frequency domain using power spectral density, or PSD. We define the PSD of white noise using the notation SNF equals N0 over 2. Here, N0 represents the average noise power present in every single unit of bandwidth. Since white noise is spread across all frequencies, its total potential power is infinite. This makes the shape of our filter the only defense the system has. This diagram shows how the wideband noise, WFT, is processed by the filter to produce a finite noise output, NFT. If we plot the power spectral density of white noise, it appears as a flat, continuous plane that extends across every frequency at a height of N0 over 2. An ideal band-pass filter acts like a rectangular window, allowing only a specific range of those frequencies to pass through. We define BT as the total bandwidth of that filter. Any noise falling outside these rectangles is physically blocked, preventing it from reaching the demodulator. By applying this specific filter, the receiver successfully converts a theoretically infinite noise problem into a finite, highly measurable quantity. To find the total noise power that actually enters the system, we calculate the total area of the noise that successfully passed through the filter. Since the noise height is N0 over 2, and we have two mirrored bands for positive and negative frequencies, the calculation simplifies. The proportional logic is straightforward. If one unit of bandwidth contains N0 noise power, then BT units of bandwidth contain N0 times BT power. This gives us our final formula for filtered noise power at the output, N equals N0 times BT. We have now mathematically proven that the total noise corrupting the signal is directly determined by the width of the receiver's filter. When we look at the complete communication system, the engineering challenge becomes a matter of balancing these different parts. The signal-to-noise ratio remains the ultimate measure of quality, constrained by two opposing forces. At the transmitter, signal power is restricted by hard limits of cost, hardware capacity, and interference. This is why receiver design is so critical. It is the point where the band-pass filter is used to surgically limit the noise denominator. In a world where white noise is everywhere, the survival of a signal depends on the disciplined application of bandwidth limits.